from Engineer Ashok Dahal. Before starting technical presentation, I would like to introduce our speaker for today. Ashok Dahal is geomatics engineer working in the field of applied science. His research uses geospatial, artificial intelligence, and geodetic observation for multi-hazard modeling. He is developing methods capable of extrapolating beyond the realm of observed data, primarily focusing on influence of climate change and geophysical processes on the regional and global scales. This is especially valid for data-sparse regions such as Nepal, which have been his area of research for the past 6 years. Most of his research is on the junction between geospatial data and deep learning, natural hazard, and statistics. Engineer Dahal completed his Bachelor of Geomatics Engineering from Tribhuvan University in 2017. Then he completed his Master in Geo-Information Science from ICT, Netherlands, University of Twente in 2021. Currently, he is a PhD candidate in University of Twente, ITC, Netherlands, as well as he is visiting PhD at Jet Propulsion Laboratory, Caltech, NASA. Without any further delay, I would like to welcome Engineer Ashok Dahal. Ashok Dahal, welcome to Geo-Series episode 11. And thank you for joining this episode. Most of us are from Nepal, so the episode we can run this episode in both Nepali and English language, whichever is preferable. So without any further delay, I would like to hand over this floor to Ashok Dai. You can present your content, and I would like to hand over the floor to you. Thank you.
Thank you. Thank you. Maybe I can share my slides first and start talking. Yes. Do you see my slides?
Yes.
I think this way I don't see anyone. So यसरी स्लाइड सेयर गर्दा हुन्छ होला है?
हुन्छ दाइ, हुन्छ। अनि एउटा कुरा चाहिँ हामीसँग एप्रोक्सिमेटली हामी 2 घण्टाको सेड्युल प्रोग्राम छ। अब यसमा हामी सुरुमा चाहिँ प्रेजेन्टेसन सुन्छौँ, त्यसपछि चाहिँ हाम्रो Q&A सेसन हुन्छ पछाडि। अब 2 आवर्समा हामी जतिसम्म त्यसलाई म्यानेज गरेर गर्न सक्छौँ, त्यही नै भन्न चाहेलाई। हुन्छ।
प्रेजेन्टेसन त मैले 1 घण्टा भन्दा धेरै जाँदैन होला, त्यसपछि 1 घण्टा Q&A प्लान गरौँ, तर आई थिंक पुरै 2 आवर्स हुन्छ होला। अनि थ्याङ्क यू फर इन्भिटेसन एनजिएसलाई अनि ओएसयू नेपाललाई पनि। आइ एम भेरी ह्याप्पी टु प्रेजेन्ट हियर। अब आजको टक चाहिँ आई थिंक इट विल बी अन जियोमेटिक्स, नेचुरल हजार्ड एन्ड नेपाल। मोस्टली टाइटल चाहिँ मैले जियोमेटिक्सकै बारेमा बोल्छु भन्दा पनि इट्स हाउ जियोमेटिक्स क्यान बी युज्ड अन नेचुरल हजार्ड्स इन डेटा स्कार्स कन्टेक्स्ट लाइक नेपाल, लाइक जहाँ चाहिँ हामीसँग रिजनल स्केल मोडलिङको लागि राम्रो डेटा उपलब्ध छैन, त्यस्तो कन्डिसनमा चाहिँ जियोमेटिक्स प्लस स्ट्याटिस्टिकल मोडलिङले कसरी हेल्प गर्न सक्छ भनेर आई ट्राई टु say some things that I know, but it doesn't mean that I know most of the things. So maybe we can start. So already, give me a second. It's not more. So goes to slideshow. Slideshow. Okay, so a bit about me. Agi Thakurle already introduced, but I think it's better if I say some things about my background. I did my geomatics engineering from WRC in Pokhara in bachelor. So we mostly studied geomatics, remote sensing and stuff like that. Then I did my internship in Asian Institute of Technology in Thailand. I was there for 2 years. So I went for internship initially, then I started working there. And then there I worked mostly with Professor Sunji Murai from Japan on GNSS data analysis and stuff like that. And I was also involved as a software developer for other projects because my time was mostly with him for 2 days a week, but remaining days I was working as a software developer for other projects from World Bank and Asian Development Bank. Then I thought, oh, it's interesting to use geomatics, but I want to understand more how we can really use it because I was mostly doing the geospatial software developing and data analysis, but I didn't really understand what those data mean. So then I went for a master's at ITC with Case Van Western. There I did my master's for 2 years. My master thesis was on improving the quality of digital elevation models in Colombia and in Dominica using the data from Austria, which was LiDAR dam, which is very good. And then we said how it can improve the quality of flood modeling. So we were working on improving geospatial data, but to understand how does it improve physical process or hydrological process. So that was quite a nice thesis. That thesis got the best MSc thesis in Netherlands for 2021. Award they gave some money. It was cool. Then I joined my PhD at ITC as well, but this time on seismic hazards, so mostly on earthquake-induced landslides. So both earthquake and landslides. And also during my PhD, I'm working on climate change scenarios to see how the climate change will affect landslide hazard in Nepal, but with more geospatial context, not in a slope scale geotechnical level study. So I'm not going to one mountain and doing very detailed geotechnical study, but I'm mostly doing geospatial modeling for large scale, like half of country or 75% of Nepal. So during my PhD, I went to Saudi Arabia for 6 months because, as you know, I'm not a geophysicist, so I didn't really know how to model earthquakes and things like that. So technology cost, it's quite cool actually. You can also go there for 6 months if you guys like. You can apply. It's a nice place in Nepal. We think Saudi Arabia, but it's way better than most of the countries I've been. So it was very interesting experience. Then I was back in the Netherlands. So I did my PhD for almost 3 years now. And now I'm at Caltech and JPL for another couple of months to do more on remote sensing based analysis of Turkey earthquake in this case. So me and geomatics, like people might ask, why you are a geomatics engineer? Your field is not really earth science. You are not. Why are you working on modeling and other stuff like uh, mapping and modeling earth system sciences? So this is a role picture I take at JPL. So this is called surveyor role. I used to feel bad actually during geomatics engineering, like when I was studying in WRC, for the civil engineers or other people from campus tell us surveyors, and then we used to get mad. But it's nothing to be mad about. I think it's quite a important um, important job. Like being surveyor is where all starts. So if you don't know, geodesy is the oldest of the earth sciences. So this is where the whole earth science starts. So it's still quite a cool science. So now getting more. So my research is in between these three things, so mostly geophysical hazards, geodesy, and remote sensing, machine learning, and deep learning. Um, small, tiny piece between these Venn diagram. I'm trying to do it. It's not really I'm doing, but I'm just trying to understand those things. So today, let's see what I'm going to make you bored with. So I have a few things to talk about, but in these next slides, you'll be bored progressively until you sleep. Then we can stop talking. So mostly we'll talk about ground motion simulation, topographic amplification, explainable AI, transformers, and then post-seismic landslide hazard modeling and extreme value theory. So it's a bit more of a statistics and what I'm doing at JPL and what I will do afterwards, like what is my next couple of months, at least next year's research plan. So first, let's start with the ground motion simulation. If you know Star Wars, you know what do I mean. But if you don't know the Force Awakens, like it's a ground motion. So there is a extremely high amount of seismic wave energy traveling towards the mountain in Nepal in 2015. So we tried to simulate this and try to understand what does it do to the landslides. So why do we simulate an earthquake? Why not just take a seismometer and then use that data? Is because uh, as again, it's a spatio-temporal process. So what happens is when you move from one location to another location, the ground motion changes. So in an earthquake, the amount of shaking that you get changes from location to location. Like if you go up in the mountain, or if you are in the valley, or if you have
Hello. Hello.
हजुर हजुर सुनिन्छ सायद उहाँको नेट चाहिँ केही भयो जस्तो छ
Okay.
मिनवाइल एउटा साथीहरू सबैलाई रिक्वेस्ट चाहिँ यदि तपाईँहरूको नाम चाहिँ आफ्नो ओरिजिनल नाम होइन भनेपछि हामीले चाहिँ बाध्य भएर तपाईँहरूलाई चाहिँ यो सेसनबाट चाहिँ हटाउनु पर्ने हुन्छ कृपया आफ्नो नाम चाहिँ राखिदिनु होला है अरू साथीहरू पनि कोही जोइन गर्न खोजिराख्नु भएको छ भने चाहिँ मेबी उहाँहरूको नाम चाहिँ
I think I lost my connection. Do you know where I was? No? No?
Hello. सुन्ने छ दाइ?
हजुर
Do you know where did I lost the connection?
In the third slide, I think.
Do you know what I was talking about?
Maybe related to second line. I don't know. You were talking about like the shaking differ from location to location.
Okay, I know
Yeah.
what I was saying. So yes, so the ground motion usually depends. So I'll just keep it like that so that it's better. I can still see if you guys are there or not. So yeah, when you move from location to location, the ground shaking will change, and that will differ on the landslide. So what we want is we want to know what will be the ground motion at each landslide, so we can better model them. Because if you don't really know what really happened in particular locations, you are obviously going to make mistakes. And also, the landslide science community always have been using something like big ground acceleration or big ground velocity, but they don't really know. We don't really knew which were the best combinations or best parameters to use. So we were trying to understand that. So for that, I tried to simulate 2015 Gorkha earthquake in Nepal. So it's quite a big earthquake, 7.8 magnitude. And if you look at the CMT center, it's quite north of Kathmandu. This is a bit different from epicenter because it is the centroid of the energy release. So it's a bit shifted than Gorkha, but it's kind of, you can think of it as epicenter. And then this is the simulation extent, the black line, which is quite big actually. So 1, 2, 3, 4, almost 4 degrees and 4 degrees in latitude and 4 degrees in longitude. So this is like the mesh itself is also 30 kilometers, 35 to 40 kilometers deep. So this is quite a heavy computation. And then we simulated the earthquake, but the problem is we have very few stations of recorded ground motion. So we have 1, 2, 3, 4, 5, 6, 7, and this is not really enough to validate it. So there comes geodesy and remote sensing. But before that, I'll also show the landslides. So if you see the black dots here, those are the landslides. There were around 25,000 landslides in that earthquake, manually mapped by someone. So we used that data. Then this is like seismic wave. We check 4 different models because there were 4, but we didn't really know which one is the good one. And then we found one is maybe better, but it's not really enough to say anything. Then what we did is we did the INSAR processing. So we have pre-event and post-event interferometry. So LOS2 data from JAXA. So we use radar data to identify how much the surface was displaced before and after the event. And then we projected our simulation to the radar direction. So because if you already know INSAR, what happens is with the INSAR you get the velocity of the smallest movement, like 1 millimeter movement in the direction of the satellite, so you can measure that. So we use that information, but it doesn't give you a 3D displacement. For that you need more geodetic observations, like more GNSS based observation. But with INSAR you can get the displacement in towards the or away from the satellite. So that's what we did. We projected our simulated displacement towards the satellite and see which one had the best correlation. The model from Waitel 2018 had the best correlation. So we say, okay, she's a good model compared to others. If you see the plot, and then we can see how does it look like. Okay. So the earthquake initiated here. This is Kathmandu. Then it moved towards east. Most of the energy was moving towards east, meaning that there was less damage in west of Gorkha compared to east of Gorkha. So we have most of the damages in here in Sindhu Paljok and upper part. So this is mostly because the focusing of the energy was towards that direction and also towards southward. So this is how the earthquake ground looks like. This is the velocity. And then there are so many in seismology, there are so many parameters that measure the ground motion. So we have earthquake power index, PGA, peak ground oscillation, radius intensity, a lot. But these are the formulas to calculate them. Then we estimated all of them and made a statistical relation, which is we try to, like, if you know the correlation coefficient, it works in 2 continuous variables. Continuous variable means if you have something 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 or 0.001, something like that, if both of them are continuous, you can use it. But here ground motion is continuous, so you have 0 to infinite values or minus infinite to plus infinite values. But with landslides you have this dichotomy. You have there is either a landslide or there is not. There is not in between, or there is no other things, like it will not be 2.5 landslide. That doesn't make sense. So then there is something called mean biserial correlation. So it works between like landslides, which is absent or present, and then other continuous variables. So then we see many correlation coefficients for different slope angles. So we have slope between 10 to 30 degree, 30 to 50, 50 to 70, because the response of topography will be different in different slope angles. Then what we could find mostly is that traditional approaches that the people in landslides were using were not that really good. There were other things like DRS. I forgot what that means, but it's in the equation. DRS and then there is one more. So those were performing way better than traditionally thought good observations. Then we also look at Moran's High. So if you don't know what Moran's High is, it's a it's the core of geospatial science. It's the core of geostatistics. So what does it do is it looks at the spatial correlation at a location. So this is a bivariate one. So it looks at how correlated they are, especially. So if you are looking at a certain location, you want to see how everything around me is correlated with me. So for a good example, like Moranzai is mostly used to find the clusters of disease and cluster of other interactions, or you can also find where, let's say in case of Nepal, you can find um, the business centers or things like that. So here we try to find the landslide centers. We try to see how the landslides are correlated with the ground motion, and also we observe that the traditional parameters do not really explain them well. Then we did modeling. So for that we did a variable selection. We tried to find which are correlated, then remove it, and then selected top 10 variables that we can use to model it. And then our final conclusion was by using the simulation and using multiple input variables, multiple input data set to our model, we cannot increase the true positives, we cannot increase a lot on the model predicting where the landslides would be, but we can decrease the false positives. So we can decrease where there is no landslide, but the model says there is a landslide. That is quite important in case of a earthquake event, because you're doing rescues and you're mobilizing the resources. So you want to have as good prediction as it can be, because if there is no landslide and the model says there is landslide, and then you have to divert 50 kilometers, then it's a waste of resource, and then by that time you could have helped someone else. So that's the importance of it. Now, coming back, I think this one I'll skip because it's not published yet, so it's better to not show something that is not fully available. But this is also trying to understand how the mountains really interact with the ground motion. It will be available soon. Now, coming to the modeling, so this was a statistical model, so we could explain what it is. But the problem is they are not really that good on predictive capabilities. So because our process is highly non-linear, we have a very big study area, then we could use machine learning because we have a lot of data. But the problem is we are trying to do some science. So we want to understand how or why our model predicts something that it is predicting. And with AI, the problem is it has a high performance, but it's not really explainable. You cannot really find out why it is doing so. So we try to build a model that can be explained for landslides, so that when we say, oh, there will be a landslide during an earthquake event, then we can understand why the model is thinking that, or at least be rational about it. If the model is predicting landslides in, let's say, Kathmandu Valley, inside the valley near Ratna Park, doesn't make sense because there is no slope to fail. So that's what we try to do. If you like Harry Potter, it's called data science, not data magic. So you have to be able to explain it. So how did we do that is, there was a scientist called Shapley quite a long time back. He made a theory in game theory. Now it's known as the Shapley explanation values. So sub values, what does it do actually is, I'll not go on detail on the math, but so if you have a football game, let's say El Clasico, there can be two outcomes. Either your team can win or lose. But one football match is not a one-man show. Like you cannot win a match by one person. There will be always either positive, like some players would be helping, or some players would be just doing fouls and not helping. So what this value tries to do is it tries to understand or explore the role of each player. So if it is Barcelona, it will look at Messi, to look at Neymar and say, okay, Messi contributed this much to this game, Neymar contributed this much to this game, someone else did so many fouls and he contributed negatively, something like that. So it gives a score. For each player, each variable, it gives a score. Also for the same team with Real Madrid. So what happens now is for earthquake-induced landslides, it will look at the slope, it will look at the aspect, it will look at the topographic positioning index, things like that, and then say, wait, the slope had the highest role, or the ground motion had the highest role. The other factors like NDPI didn't have a better role, things like that. So that's how it assigns the variable. Then we built a AI-based model where we tested it quite vigorously. So it's a reference model to see the AUC is this curve is, you just have to understand the higher this curve goes, the better. So the AUC value is higher, it's better. So then we did the cross validation. So random cross validation is we're just selecting random locations. In the spatial cross validation, we're looking at we're training our model in one location and then predicting in the other location to see how it performs. So it was performing quite well. If you don't know, this is a confusion map. It's a bit confusing, but so all the so here all the blue, light blue and pink are good ones. The one with the red and dark blue are the bad ones. We also have quite a lot of bad predictions, so it's not a perfect model. And then we looked at it, and then it shows the amount of clay has the highest role for landslides in Nepal, followed by slope and the peak ground velocities, like how much the ground is moving is not actually the first most important variable, it's the third one. You might say, oh, but there was no landslide without earthquake, but the clay and slope create a condition for landslide to happen, and then when there is a ground motion, it just happens. So those two variables are also quite important, and then we have a whole lot of variables which have a mean. This is a mean behavior, right? So it's not depending on one location; it's everywhere. And then we could look at variable importance for individual mountain. So you can click on a mountain, you can look at the mountain, you see this is the starting probability. So it's in the beginning, it's 50-50 almost. There is slightly less chance of having landslide, so 49, and then a slightly higher chance of having landslide in Nepal. But then you can either increase the probability or decrease. So there are very many variables that can either increase or decrease, and you can get at, let's say, final probability of 0.31 or 0.73. So it's just a simple probability. Then we built a web application where you can go to any mountain in Nepal, most of the mountains in Nepal, click on it, and then see what is the probability of having a landslide there, which variables are controlling it. So this is for earthquake-induced landslide. So if you want to mitigate, if you want to not have a landslide, you can just look at this curve and see, oh, it's mostly caused by, it's a slope, things like that. And then you can do a further detailed investigation there, depending on the project. Right? If you're building a hydropower, it would be better to do a proper geotechnical investigation than trusting my results. This is what we did. And it's a published article. You can find the web link and play with it later anyway. So now this model, what it does is we're looking at a constant still. So as I said before, one variable does not really explain the landslides very well. So what we try to do now is to look at the time series. So we are trying to understand how the earthquake time series, like, because when there is earthquake, it's not like it comes like it's not moving, it moves a lot, and then again not, it's not like that. There will be certain moment, like it will be 1 minute or 2 minutes of shaking. So you'll have the ground shaking for quite a long time. So you want to see how that ground shaking actually causes the landslides, because it's not one variable, it's not one parameter that controls, because if you have ever seen a seismic waveform, if you have ever seen a seismogram, it looks quite noisy. It's like you want to also use all these like movements. So that's what we try to do with something called transformers. It's published last week actually. So if you don't know what transformers are, this is so initially our paper's name was Transformers More Than Meets the Eye, but the publisher didn't want to have the copyright infringement, so they removed it and they changed it to full seismic waveform analysis combined. Very boring, but anyway. So the Transformers are quite nice cartoons, and also they have quite a lot of movies. And there is a Linkin Park song actually, Transformer More Than Meets the Eye. So I'll not go into detail how we develop the model, but what does it do is it takes the time series from earthquake, and then also it combines slope and other things from Nepal mountains, and then tries to predict. That way we can predict quite well actually, like 94% we are correct, almost with accuracy. But if you are looking at the AUC, by just using static variables, we're not that good. But when we keep increasing, it goes really well. So here you can see in different, so this ACC is the accuracy. So you can see it's almost 90% accurate in most of the time. It's very interesting. And if you don't know what these are, it's okay, but they are mostly useful if you are doing machine learning on any kind of data, but especially in geospatial data, these IOU and FM score are quite nice one. So then here we tried 4 different cases. One, we just model with the waveform. We just put the waveform. We don't give any information about terrain, because when we try to simulate the waveform, we already know the terrain. Then we use with the peak ground velocity. Then we build another with terrain, geology, and waveform. Another is PGV, terrain, geology. So what we can see here is actually with just the PGV and PGV plus terrain plus lithology, the model is just giving probabilities most of the locations. So if the model doesn't know where the mountains are, saying it will be everywhere, but when you introduce mountains, it will say, okay, it will be everywhere there is mountain. So it's not really that nice. So it's not giving high probability. It's always between 0.7 and 0.4. So you don't really know if there will be a landslide or not. But with the full waveform, it's giving very precise results. Like if you see the panel here, it's giving quite a panel C. If you can't see my mouse, it's giving extremely well probability mapped around the locations where there were landslides. So it's quite interesting. And why? So as I said, it's data science, not data magic. So we try to understand why, and then we say, okay, we look at the locations that are correctly predicted with the PGV and also with the time series. Only ones that are predicted correctly with the time series in left and right. And if you see in the locations where both of them were correctly predicted, it was not only looking at the peak arrival, like the maximum of the ground motion, but everywhere. It has a higher score. Like it gives attention, a lot more attention everywhere. And this is like east, west, north, south, and up-down component. So the east-west component, because the surface moves in 3 directions, right? So the east-west component has the highest influence. That's true because our ground motion, rupture, as I showed you in the first video, the ground motion moves towards east, towards Kathmandu from Gorkha. So that's why in the east-west direction, facing mountains, the damage was much higher. So if you look at the seismic waveforms here in the gray and the red and green are the explainable scores, you see that in the locations where these predicting well, when you're using PGA, the highest scores are around PGA. But when you go towards the other locations where the PGA-based model cannot really give right answers, it's looking all everywhere. Like here where the surface wave arrives, where the P wave arrives, where the S wave arrives. So this is quite an interesting thing. And then we try to see where did it improve. So it's more geospatial analysis. We classified the landforms, we classified all the mountains, and try to see where did it improve. So it improved in locations with less slope. So in the steep mountain, like not super steep cliff, but in a steep mountain, you can just look at it and say, okay, if there is a certain ground motion, you'll have a landslide. But when it's more problematic when it comes to hilly areas because it's more difficult to classify them, and also less shaking. So if you have more shaking, you can always say, okay, there will be a landslide. But if there is less shaking, it's more problematic to identify them. And in the valley slopes, so near the valleys, so if you don't know what valley is, anything can be valley. Like if you have a small plain in between the mountains, so it's not only Kathmandu is valley. So in the slopes nearby valleys and stream slopes near the river, those slopes were way better predicted with using the full time series than other locations. Open slopes are pretty much same. And now, so this is up to an earthquake, right? We have just talked about what happens when there is an earthquake during an earthquake. That's for what, 10 minutes or 1 hour, at max 2 hours. After that, it's not really a problem anymore. The problem is more on the rescue and helping people and stuff. So now we try to see if there is a big earthquake, does it pose a risk? Does it have a risk of having more landslides in the next couple of years? Because in Nepal earthquake, what happened was we had an earthquake in May, Boisak, then we had, like after 3 months there was monsoon and it made the situation worse. So this is something called cascading hazard, or not really cascading, it's conditional. So it's a chain of events, right? So here we try to understand how did it happen in Nepal. So a bit of a background is not all landslides are equal. So if you have red animal farm, like all animals are equal, but some animals are more equal than others. So it's the same. All landslides are equal, but some landslides are more equal than others. Because if you see, because we've only talked about probabilities, 70% probability of having a landslide, but 70% probability doesn't mean anything. It means this could have the 60% probability, the other one could have 80% probability, but the damage that they cause is different. So what we try to do is we try to model also the size. So not only the probability of the landslide, but also the size of it. And for that, we built a model and not talk a lot of jargon here, otherwise it will make you sleep. And I guess half of you are already asleep. So what happened at the end is with this model, we could predict the susceptibility. So how much the probability a certain location has on having landslide. The area density is if there is a landslide for a certain pixel, for a certain mountain, how much percent of that location will fail, like we'll have the mass wasting. Then we multiply these two to get the hazard. So if you look at it, just looking at the susceptibility in co-seismic period and post-monsoon, it looks almost the same. But when you look at the combination of two, the hazard is decreased, but still it's quite a significant one, right? So in 2015, during the earthquake, we had a lot of landslides that were also big ones. Then the rain came. During the rain, also there were a lot of landslides, but less big, like less in number, less in density, but it was quite a lot. And then 2016 came. It became more sporadic, very few. And then 2017 came. It was still similar, not really low, but still quite a few, not really a significant problem. In 2018 had more landslides. I think it was because of the higher intensity of rainfall, but it was more landslides that we don't know why. This you can plot it as a control plot. So you have the size of the landslide, the probability. So if anything that is here in this red, like towards the left, be problematic. So during the earthquake, it goes quite long and then it slowly decreases. So after every year, it decreases, the hazard decreases, still it's there. Now we come a bit more to extreme value theory. Most of you, I guess, are not statisticians, so you will not know what it is. So what happens is, I guess everyone knows what normal distribution is. So the normal distribution, I can just zoom in. So the normal distribution looks like this. It's a bell-shaped curve, and most of the machine learning models or statistical models have inherent assumption that they are normally distributed. So they are like this, but landslides are not. Landslides are never normal distributed. They are, you can say log normal, but they are something called extreme value distribution. So you will have a lot of landslides with a small size, but when you have bigger landslides, they are very dangerous, but they are less frequent. So they will be here in the extreme tail. So it will be more landslides with small size, few landslides with large size. But what happens is when a machine learning model works, it tries to always predict nicely in the mean, but it doesn't really predict well in these two extremes, two other sides, like too far away side. But for landslide, that's a problem because when you go towards big landslide, those are the ones causing problem. If you have very small landslides in a mountain where nobody lives, it's not a problem. But when the whole village starts to move, that's a problem. So, but still few the models that we are building do not respect that statistical theory. So they do not really model well in that thing. So we cannot really use normal distribution. Before also in this model, we are using log version of it. So we use log normal distribution, but that's also not really a good distribution. So we use something called extreme value theory, which is paranormal distribution, but not really paranormal. So what this is mostly the fun things. So but the problem is I was talking about earthquake till now, but we have to talk about landslide. Give me a moment, my phone alarm is going off. Sorry, it's 6 in the morning, so if you have watched The Office, you know what I mean. But so what happens is for the extreme value theory, we need a lot of big events. In earthquake, like the landslide in Nepal is 2015, so we don't really have many events to build a reliable model. So what we did is it's more of a theoretical development, so we can change the data. So instead of earthquake, we used rainfall. We have a rainfall map of Nepal, rainfall-induced landslide map of Nepal for the past 30 years. So we used that 30 years of data to build something called the extreme value theory based model. A bit of math, I think it's quite important here. Maybe I can show it like this. So landslide hazard at the location is probability of union, so is by space and time. Having a landslide, this is our spatial domain. A landslide equals to 1, so you have a landslide and area exceeding a certain threshold. Let's say the landslide area being greater than 0 or greater than certain probability. So what we are looking at is for a particular location, we are looking at for a given landslide area threshold. So we are looking at if the landslide will be bigger than 1 square meter, and it has to occur. Like we need to know the probability of the landslide and its size. So the landslide itself has something called Bernoulli distribution. So it's binomial. So you have either there is a landslide or there is no landslide. So you can model this quite easily. For the area component, which is more difficult, where you have landslide area in space and time, given that the landslide area is greater than 0, so you will not have a landslide. Or if it is not greater than 0, theoretically follows something called extended generalized Pareto distribution, given that it has these parameters. So it has 3 parameters: shape, location, and magnitude. But it doesn't matter. You don't really have to understand that. But what does it mean is it follows a extreme value theory, and to identify the intensity given that is u2 1 minus GDF of that function, which is this blah blah. But what I'm trying to say here is your model should look like this. The landslide size model should look like this, and it has different parameters to learn from. And you need to identify, at least you can keep a couple of them constant, but if there is 3 parameters, you need to at least change 1 or 2. So that's what we did. This is our function that we need to train our deep learning model is on. So it's a combination of these two. So it's a joint model. The joint model predicts 2 probabilities at the same time. So this is our function to train the model on. And sorry, this slide I made initially for different audience, so it became a bit complex, but you don't have to worry about it. It's just trust me what I say. So then what we could do is, then we had the rainfall data, so we calculate the return period for different rainfall events. So we have 5, 10, 15, and 20-year return period of rainfall. And then we have 5% of failure, 50%, and 95% of failure. So based on the past 30 years of observation, we want to see what is the chance, given a 5-year return period rainfall, there will be a landslide bigger than 5% of the observed landslides in the past 30 years. So it doesn't really mean 5% of the mountain failing, it means 0.01% or something, but just looking at the 5% of the observed data. So we're looking at what is the chance of having a landslide that's bigger than at least the 5% of the entire landslides that happened in the past 30 years. It's quite high. And when you go to 20-year return period, it keeps increasing. Everything is increasing for 20-year return period actually. So when you have bigger storm, the landslide hazard will increase. And here very high, you might think, oh, it's guaranteed to have it. No, it's just 50 or more percent of hazard. It's not really probability. And then another is probability of exceeding 50% period. So being bigger than half of the landslides is, for 5-year event, it's quite low. It's mostly high, so 25% probability, not really a big problem. But when you go towards 20-year return period, it keeps increasing. It gets more dark, more red. And the same, like probability of exceeding the landslide size greater than 95%, it's virtually none. And then it keeps increasing to low to medium, like none to very low to medium, when you go towards high return periods. And if you look at the upper part here, there is a distinct green color everywhere, which is the Sabarmati and upper mountains. This is for 2 reasons. First is there is very high standing cliffs, so there is no soil to have a landslide. And the second is when they mapped the locations on very high mountains were not really visible most of the time. So maybe they missed mapping those landslides, and then you don't really have good data to train from, so the model is doing some wrong predictions. So I've not really trust the result there, but it's at least my understanding is it's mapped quite well, but it's just that there are not many landslides there when you go to the snowy mountains. So this is the prediction for climate change scenarios. So what happens is, this is the current hazard. This is what happens now. But if you want in next 80 years, due to the climate change, we have different climate pathways. So in the next, let's say, couple of hundred, up to the end of the century, from 2020 to 2100, average landslide hazard changes like this. So if it is blue, it decreases. If it is gray, it doesn't change. If it is yellow or gold, it increases. So you can see in the in more not fossil fuel development, like in the SSP 245, which is a cautious development stage, we still have increase in landslides in Nepal. It's increasing quite a lot. It's decreasing in the upper mountains. It's not really increasing a lot in the upper Himalayas. And when you go at the SSP 585, which is a fossil fuel development scenarios, it increases everywhere. Also, its intensity becomes quite high. So if you see between these two, you see that the yellow regions increase a lot. So if we do more fossil fuel development, we'll definitely have higher landslides in like more than 100% increase in landslides in most of the return periods in average in the next century. So, but there are some problems here. Limitations is that the climate change scenarios are not always good. So we use 30 different climate change scenarios, and this is the average result. So we don't really know the future exactly. Like we don't really know this much rainfall will be there, but this is the estimation, right? So this is the estimation based on estimation. So I'd take it with a pinch of salt, but you can say that it's increasing fairly with the climate change scenario. Now, if you are sleepy, don't worry, we're almost at the end. So this is what I've done up to now. So what I'm doing now in JPL is we have now talked about the landslides during an earthquake, after an earthquake, and after 50 years. This we can actually change with the earthquake scenarios, and the results will be different, but the model will be the same. But what we have not done is we have not looked at how the earthquake changes the pattern of deformation or pattern of landslides from before the earthquake setting to after the earthquake setting. So for that, I came to JPL. So what we are doing now is trying to understand the pre-event and post-event deformation. So for that, we didn't have a lot of data in Nepal. So we moved to Turkey, where there was a big event in 2023. And then we take past 5 years of in-site analysis for the whole country of Turkey. So it's a lot of data, couple of terabytes, not couple of, actually like tens of terabytes. Then we take that data and then we try to understand what the earthquake changed and what happens now. So how such a big magnitude event had changed the deformation patterns. So did it accelerate the mountains deforming, which will cause a landslide later on, or did it stop, or did it change the spatial location of them? So I'm doing the inside processing now, but let's see. So this is mostly bringing back the geodesy component in my PhD research. So after I finish here, I'm mostly now working on. So still, we have not really talked about the physics behind it. So I'm now working on bringing the physics in a regional scale. So we are trying to model using neural network the physical process like movement process, but there are the actual theory on landslide initiation and flow. So when the landslide occurs and it moves, is not fully compatible with the system that I'm solving. So I'm working on that. So this is something cool. This is an animation using something called material point method. It's advanced. And neural network, we try to solve the breaking of a break. So this is not real. This is just animation, but this is done with physics. So if you have watched Frozen, like the snow falling, this is also done with physics. So we know the properties of the snow, then you flow it, and then you do simulation. So this is what we did with the blade, but now we are trying to do it with the earthquake in this landslide. So you will have this force instead of someone pulling, it will be ground motion, and then we look at how does it break the mountains. So that is something that I'm working on, like halfway done, but still it's a long way to go. So I think it's almost an hour. So yeah, if you have questions, if you are sleeping, thank you for not sleeping. I guess it's already 8 in Nepal. So if you have questions, I think I can take the questions now.
Thank you, Ashok Bhai, for your presentation. I hope everyone enjoyed this beautiful session about landslide and disaster, especially focused on Nepal. We have a question in chat box from Silva Kuidala. Our question is about use of distribution on this research. In context of, I guess this model is based on Gaussian distribution. In context of Nepal, where data gaps are usually high, how did you deal that? Have you done any uncertainty test with Bayesian approach? It would be great to see your results, if any.
I'm not sure which model you're talking about, Gaussian based, because the extreme value theory, it's not a Gaussian model. It's called extended generalized Pareto distribution. So its distribution function is, so if you're looking at the CDF, it's 1 minus 1 plus these 3 parameters. So this one is not really based on the Gaussian distribution. The previous one is log Gaussian, so it's a log normal distribution. There are data gaps, of course, but in terms of landslide, it's quite good actually, because we are not really looking at very small landslide, like 10 meter. So because they are mostly mapped using satellite image or orthophoto data and manually verified, there are ways to validate them. So there is something called completeness indexed. So this is developed by Hakan in our group. So you can look at the completeness index by checking the quality of data, and that's what we do before modeling. So the inventories that I have had quite fairly good completeness index, and we assume that it's complete. We don't really assume that it has data gaps anymore. But yeah, there could be locations where we didn't really map them, but then we didn't really do the uncertainty propagation, because that's a completely different research of doing a full uncertainty propagation. I guess that answers the question.
Again, another question regarding same.
Confused with the level landslides, how big size must with the respect to area, rockfall, topple. So this is mostly the shallow landslide. So it's not really the rockfall or topple. It's mostly the shallow landslides caused by earthquake, not the rockfalls. I don't think there is really mapped in rockfall.
Okay. From Tek Bahadur Chetri, have you published the data set and codes in your paper?
Yes. So if you go to the paper, there is always a link to Zenodo where we have data set, and mostly the codes are also there, but also in my GitHub account.
Okay. If anyone have question, please leave it in the chat box. We have time to respond it. So मेरो चाहिँ अलिकति एउटा क्वेसन रिलेटेबल हुन पनि सक्ला नहुन पनि सक्ला। मैले खास चाहिँ बुझ्न खोजेको चाहिँ यो ल्यान्डस्लाइड हामीले भन्ने बित्तिकै अलिकति मोस्ट लेस फ्रिक्वेन्टली अब्जर्भ हुने ड्राई ल्यान्डस्लाइडको पनि नेपालमा अलिकति प्रब्लमहरू देखिरहेको हुन्छ। जस्तो हामीले सिन्धुपाल्चोकको मार्क्समा अलि अगाडि गएको थियो, जस्तो हामीले प्रिडिक्सन गर्दाखेरि एप्रोचहरू चाहिँ ड्राई ल्यान्डस्लाइड अथवा मनसुन पछि हुने ल्यान्डस्लाइडमा फरक हुन्छ कि अथवा के हुन्छ यसमा?
त्यसमा के हुन्छ त भन्दा मेन प्रब्लम चाहिँ तिम्रो ट्रिगरिङ मेकानिजममा डिपेन्ड गर्यो होइन। ड्राई ल्यान्डस्लाइडको ट्रिगरिङ मेकानिजम र स्यालो अथवा रेनफल इन्ड्युस्ड अथवा अर्थक्वेक इन्ड्युस्ड ल्यान्डस्लाइडको ट्रिगरिङ मेकानिजम चाहिँ डिफ्रेन्ट हुन्छ। त्यसले गर्दाखेरि चाहिँ प्रेडिक्ट गर्दाखेरि हामीले युजली ड्राई ल्यान्डस्लाइड अथवा डिप सिटेड ल्यान्डस्लाइडहरू अथवा रकफललाई चाहिँ यो मोडलमा एज्युम गरेका छैन। किन भन्दा तिनीहरूको इन्ट्रिन्जिक बिहेभियर, तिनीहरूको चाहिँ जुन प्रपर्टी हुन्छ, कसरी फ्लो हुन्छ अथवा कसरी इनिसिएट हुन्छ भन्ने चाहिँ डिफ्रेन्ट हुन्छ। त्यसले गर्दा what we try to do mostly is the ones that are caused by earthquake, the shallow landslide that are caused by earthquake, and also due to precipitation, like extreme precipitation, but not the ones that are caused by the dry events or the groundwater change or things like that.
Okay, thank you.
मेरो पनि एउटा क्वेसन छ सो मोडलिङ गर्ने बेलामा चाहिँ त्यो नर्मली ल्यान्डस्लाइड एरिया चाहिँ लेस हुन्छ हाम्रो ब्याकग्राउन्डको कम्पेरिजनमा राइट इफ वी टेक दि लाइक बिगर एरिया एन्ड नर्मल्ली हजुरले डिप लर्निङ पनि गर्नुभएको छ त्यस्तो केसमा चाहिँ कसरी ट्याकल गर्नुहुन्छ ट्रेन गर्ने बेलामा सबै लाइक सबै टाइलहरू या डेटा इम्ब्यालेन्सले
टाइल भन्दा नि हामीले चाहिँ मोस्टली समथिङ कल स्लोप युनिट युज गर्छ स्लोप युनिट भनेर चाहिँ तिमीले एउटा माउन्टेनलाई एउटा युनिट बनाउँछ त्यो होमोजेनाइज गर्ने तर एनिवे डेटा इम्ब्यालेन्स त्यस पनि हुन्छ त्यसलाई चाहिँ के गर्ने त भन्दाखेरि वाट आई डिड इज मोस्टली चाहिँ तिम्रो यदि there is two approach you can reduce the background samples तिमीले चाहिँ घटाउन मिल्यो हैन नो ल्यान्डस्लाइड लोकेसन्स लाई त्यो गर्दा त्यति राम्रो अप्रोच हैन त्यसपछि the loss functions that I am using are called like if you are using binary cross entropy it's weighted binary cross entropy so you can give weight based on the observation that you have or you can use something like focal traversky loss which accounts for the or dice loss which accounts for the imbalance in data data imbalance like tackle गर्नलाई चाहिँ focal traversky loss अथवा dice loss अथवा चाहिँ तिमीले weighted loss लाई चाहिँ तिमीले रेशियो लिएर मल्टिप्लाई गर्न मिल्यो randomized data भएपछि it's not a problem तर पनि like if you want to use mostly focal traversky dice loss are quite nice or traversky loss.
Okay, thank you. अनि अर्को क्वेसन चाहिँ नेपालको केसमा लाइक हजुरको मोस्ट अफ दि लाइक ल्यान्डस्लाइडको केसमा त स्लोप एस्पेक्टहरु त हजुरले सजिलैसँग पाउनुहुन्छ रेनफल डेटा पनि आई थिंक यो सेटेलाइटहरुबाटै पाइन्छ होला हैन देयर आर लट अफ ओपन सोर्स डेटा अनि लाइक ल्यान्डस्लाइड इन्भेन्ट्रीको डेटा अनि जुन चाहिँ गभर्नमेन्टबाट आउनुपर्छ यदि कुनै डेटाहरु युज गर्नु भएको छ भने त्यस्तो डेटाहरु पाउन चाहिँ कतिको च्यालेन्जिङ भयो अनि कसरी चाहिँ एप्रोच गरिरहनु भएको छ
So inventory चाहिँ mostly we take it from the published work if usually नेपालको केसमा चाहिँ इन्भेन्टरीहरु म्याप गरेर हुन्छ अनि यदि वर्क पब्लिश छ भने you can just send an email and request them to keep the data or usually the data is already available to use गर्नलाई त्यति प्रब्लम हुँदैन तर अरु डेटा लाइक जियोलोजी त्यो चाहिँ एकदम प्रब्लमेटिक भएको हामीलाई चाहिँ युजुअली जियोलोजीको डेटा हो त्यो पनि अब जस्तो फर इन्टरनेशनल रिसर्चर जो बाहिर बसिरहनु भएको छ डेटा किन्नलाई चाहिँ तिमीले गएर बैंकको भाउचर भर्नु पर्यो त्यसपछि नेपालमै हुनु पर्यो इट्स अल्सो कस्ट अ लट अफ मनी हैन त्यो अनि दे डोन्ट गिभ यु द डिजिटल म्याप्स दे जस्ट गिभ यु लाइक स्क्यान टोपो सिट्स नट टोपो सिट्स स्क्यान जियोलोजिकल म्याप सिट्स त्यो चाहिँ एकदम प्रब्लमेटिक हो किन भन्दा जस्तो त्यही नन डिजिटल डेटा लिनलाई नै मान्छे लेट्स युएसमा काम गरिरहेको साइन्टिस्टले नेपालमा काम गर्दैछ भनेदेखि त्यो टोपो जियोलोजिकल म्याप लिनलाई नै ऊ यहाँबाट नेपाल गएर त्यसपछि त्यसलाई किनेर अनि फेरि लिएर आएर अनि हातले डिजिटाइज गरेर बस्न त आई डोन्ट थिंक एनीवन हैज द्याट काइन्ड अफ टाइम त्यो भन्दा बरु स्टडी एरिया नै चेन्ज गर्छ युजुअली हैन त्यो भएर चाहिँ इन्टरनेशनल रिसर्चरहरुलाई काम गर्न अलिकति गाह्रो भएको नि त्यो पनि वान अफ द प्रब्लम हो अनि मैले चाहिँ मोस्टली इसी मोडबाट पब्लिश भएको लिथोलोजी डेटा तथा ग्लोबल प्रडक्ट वाकिनिगन युनिभर्सिटीले निकालेको ग्लोबल सोइल प्रडक्ट्सहरु युज गरेर मेरो रिजनल स्केल स्टडी भएर स्टिल इट्स ओके टु युज कोर्स रेजोल्युसन नट रियली अपडेटेड डेटा बट इफ यु आर लुकिङ एट मोर स्पेसिफिक साइट्स चाहिँ एउटा बेसिन मात्र हेर्न लाग्छ अथवा मेलम्ची बेसिनको डिटेल स्टडी गर्न लाग्छ भने चाहिँ data you have to get it through mines and geology department and it's quite a challenge I think to get data from there and data चाहिँ जस्तो किन्ने नै भए पनि people don't mind buying it but it should be at least in digital format or you can go online and buy it no you don't have to travel like half of the world to buy the data set that I think could be improved
हो अहिले अहिले मैले पनि हाइड्रोलोजीको डेटाहरूमा त्यस्तै समस्या देखेर नै यो क्वेसन रेज गरेको मलाई चाहिरहेछ अनि डेटाहरू चाहिँ पाउनलाई गाह्रो छ थ्यांक यू
अनि या
ओके अलिकति थोरै मैले चाहिँ जान्न खोजेको चाहिँ जस्तो हामीले यदि रिजल्ट बेस्ड अन रिजल्ट जस्तो चाहिँ हामीले ल्यान्डस्लाइडको चाहिँ डिफ्रेन्ट मुभमेन्टको टाइप भन्छ भने होइन जस्तो आई डोन्ट नो डिटेल अबाउट ल्यान्डस्लाइड बट जस्तो होरिजोन्टल र भर्टिकल मुभमेन्टहरू अथवा डिफ्रेन्ट टाइप अफ ल्यान्डस्लाइडको मोसन हुन्छ जस्तो हामीले जस्तो तपाईँहरूले गर्नुभएको रिसर्च यदि त्यसमा चाहिँ जस्तो यो डिफ्रेन्ट टाइप अफ ल्यान्डस्लाइडले चाहिँ के अरे सरी अर्थक्वेकले चाहिँ ल्यान्डस्लाइडमा गर्ने इम्प्याक्टहरू यस्तो रिजल्ट बेसमा केही यस्तो आएको छ जस्तो कुनै
मुभमेन्ट एनालाइसिस चाहिँ छैन हामीले गरेको त्यो चाहिँ वो स्लो मुभिङ भयो भने चाहिँ मुभमेन्ट अलिकति मोनिटर गर्न पनि सजिलो हुन्छ होइन हाम्रो मोस्टली डेटा चाहिँ सेटेलाइट रिमोट सेन्सिङबाट आउने भएको हुनाले प्रब्लम के हुन्छ भन्दा जस्तो फास्ट मुभिङ ल्यान्डस्लाइडलाई चाहिँ त्यो मुभमेन्ट एप्रोक्सिमेसन नै गर्ने हो त्यसलाई चाहिँ मेजर गर्न मिल्दैन स्लो मुभिङ ल्यान्डस्लाइड हो भने चाहिँ त्यो मिल्छ जस्तो मेरो कलिग्सहरूले गरिरहनु भएको छ त्यसमा चाहिँ कस्तो हुन्छ त भन्दाखेरि तिम्रो इन्साइड डिफर्मेसन हेऱ्यो डिफर्मेसन टाइम सिरिज हेऱ्यो त्यसपछि यु क्यान not fully get it in 3D, but at least you can estimate कुन डिरेक्सनमा मुभ भइरहेछ स्लोप भनेर चाहिँ यु क्यान एस्टिमेट द्याट त्यो चाहिँ मोस्टली स्लो मुभिङ ल्यान्डस्लाइडलाई इन्सार युज गरेर पर्छ अनि त्यसलाई मोडलिङ पनि गर्न मिल्छ तर मेरो केसमा चाहिँ फास्ट मुभिङ स्यालो ल्यान्डस्लाइडहरूलाई चाहिँ त्यो अलिकति डिफिकल्ट हुन्छ तर मुभमेन्ट डिरेक्सन त छैन यसमा मोस्टली गर्ने भनेको साइज र प्रोबेबिलिटी अफ ह्याभिङ ल्यान्डस्लाइड मात्रै हो स्ट्याटिस्टिकल मोडलले अब तिमीले फाइनाइट लिमिट एनालाइसिस गर्यो भने चाहिँ
Another question: how convincing and plausible are your model result, especially for decision making?
So for decision making, first, I'm not sure if anyone is going to use it for decision making, but most of the things that I have done, my model results are validated. You know, we have done 3 types of validation. Like we have done spatial, random, and mostly also tenfold like cross validation. So we have random cross validation, we have spatial cross validation. So based on the data that we have with us, we have done the validation. So they are quite okay. But the problem is, if you are going to use it, you can use it for like zonation purpose. You can use it for understanding what is the probability of having landslides in a certain region or whether to build a road or not. But it's not, my results are not, should not be used for things like if you're building a hydropower or a big road, and then you just look at the map and say, okay, there is no big landslide hazard, so we can build it there. No, for that you need a detailed geotechnical studies. You need a better study, like you can identify the locations where the landslide has potential. Like you can look at the map and look at the locations with high probability. And if you want to build something, then you have to, if you want to build something in those locations with high probability, you have to do a proper geotechnical study. You have to make a borehole, you have to like bring the samples, and you have to do a proper study to mitigate them, right? It's not like we don't have the physics fully modeled. We don't really know the subsurface data sets. We don't have done the borehole studies and things like that. So you need to have more detailed geotechnical site investigations before you start building things in the red zones. But mostly in the green, like if this is less than 10% probability, I think it would be quite safe. It's not really a problem.
Okay, so we will take at most 1 to 2 questions if anyone have question.
Dick has raised his hand, I think.
Thank you for the good presentation, Ashok. Very राम्रो presentation गर्नुभयो हैन?
हजुर.
एकदम congratulations. मेरो एक दुईटा observation, like some feelings.
हजुर.
मैले पनि म पनि अलिअलि अब तपाईँसँग कनेक्ट भइरहेको छु, मैले अलि फलो पनि गरिरहेको छु होइन। अब वास्तवमा हजुरले एकदमै नेपालको विषयमा रिसर्च गरिराख्नु भएको छ, हजुरको मेन रिसर्च नेपालमै भइरहेछ, त्यो एकदम खुसी लाग्छ। अब मैले आइएम वन्डरिङ मैले लागेको चाहिँ तपाईँहरूले गरेको यस्तो राम्रो काम जुन ग्लोबल्ली जुन एक्रिडेट भइरहेछ नि, यो चिजलाई हामीले गभर्मेन्ट अफ नेपालमा बसेर काम गरिरहँदा यसलाई हामीले पोलिसी डिसिजन सपोर्ट सिस्टममा कसरी इन्टिग्रेट गर्न सकिन्छ होला, एउटा कुरा होइन। अर्को कुरा चाहिँ अब यो हाम्रो भनौँ न कम्युनिटी लेभलमा अथवा रिस्कको, हेजार्डको अथवा एक्सपोजरको अथवा भल्नरेबिलिटीको कुरा गर्दाखेरि त्यसलाई हामीले कसरी क्वान्टिफाई गर्ने, यसलाई सिटिजन साइन्समा कसरी जोड्न सकिन्छ होला। तपाईँहरूले जस्तो एकदम गरेको स्टेट अफ आर्ट काइन्डको रिसर्च छ नि, यो चिजलाई एउटा चाहिँ कम्युनिटी लेभलमा अथवा जो रेस्पोन्डर हो नि, सुरुमा डिजास्टरको साइकलमा सुरुमा रेस्पोन्ड गर्ने भनेको त कम्युनिटी लेभलको मान्छेले गर्छ, अथवा त्यो चिजलाई हामीले कसरी जोड्न सकिन्छ होला। यो मेसिन लर्निङ टु कम्युनिटी सेन्ट्रिक चाहिँ डिजास्टरमा हामी कसरी जान सकिन्छ होला भन्ने कुरा चाहिँ मैले सोचिरहेको छु होइन। अब र अर्को कुरा चाहिँ हामीले अब अलिकति डेभलप कन्ट्रीको सिनारी हेऱ्यो भने कस्तो हुन्छ भन्दाखेरि चाहिँ एभ्री सिटिजन साइन्सलाई त्यहाँ चाहिँ डिजास्टरको कुराहरू चाहिँ अवेर गराउँछ कि। जस्तो म अहिले जापानमा छु, जापानमा कस्तो हुन्छ भन्दाखेरि यहाँको सिटी अफिसमा तपाईँ आफ्नो भाइटल रजिस्ट्रेसन गर्न जानुभयो भने दे विल गिभ यु द पेपर। तपाईँ चाहिँ आउनुभयो सिटिजनमा रजिस्टर गर्न जानुभयो भने त्यहाँको सिटी अफिसले भनेको मेयरको अफिसले तपाईँलाई एउटा पेपर दिन्छ। त्यो पेपरमा चाहिँ तिम्रो यो तिमी बस्ने सिटीमा यो लेभलको हेजार्डको यो रिस्क छ भन्ने कुराको एउटा खालको नलेज दिन्छ होइन। यो चिज चाहिँ हामीले हाम्रोमा कसरी चाहिँ हाम्रो लेभलको जुन सोसियो डेमो अथवा पोलिटिकल डिफ्रेन्ट खालको इकोलोजी छ नि हाम्रो, त्यो इकोलोजीमा हामीले कसरी एडप्ट गर्न सकिन्छ होला, त्यस्तो खालको फ्रेमवर्क एकदम मैले क्वान्टिफाई गरेर भन्दाखेरि चाहिँ रिस्क सेन्सिटिभ ल्यान्ड युज प्लानिङ, रिस्क सेन्सिटिभ डिसिजन मेकिङ अथवा रिस्क सेन्सिटिभ सोसियल यो के भन्छ सिटिजन साइन्स, यस्तो कुराहरू हामीले कसरी इन्फोर्स गर्न सक्छौँ अथवा यसलाई हामीले कसरी पोलिसीको फ्रेमवर्कमा लान सक्छौँ भन्ने कुरामा पनि हामी अब यो यत्रो ठुलो रिसर्च भइरहेछ होइन। यो चिजलाई कसरी लान सकिन्छ भन्ने कुरा अब फर्दर डिरेक्सन चाहिँ त्योतिर तपाईँहरू लाग्नुपर्छ होला भन्ने मेरो फिडब्याक र सुझाव पनि मैले दिन चाहन्छु। धन्यवाद।
एकदम सुझावलाई चाहिँ धेरै धेरै धन्यवाद। आई थिङ्क त्यो प्रब्लम हो होइन। जस्तो मेन प्रब्लम के हो चाहिँ भन्दा जुन स्पिडमा साइन्टिफिक डेभलपमेन्टहरू भइरहेछ, जुन स्पिडमा चाहिँ नयाँ टेक्नोलोजीहरू डेभलप भइरहेछ, त्यो स्पिडमा गभर्मेन्टलाई पनि चेन्ज हुन इट्स नट पोसिबल होइन। किन भन्दाखेरि तपाईँको ल भन्ने कुरो चाहिँ इट टेक सम टाइम, टेक सम स्टडी टु चेन्ज इट। अनि इभन डेभलप कन्ट्रिजमा पनि त्यो युजली लाइक 5-6 वर्षको ल्याग भइरहेको हुन्छ टेक्नोलोजी र इम्प्लिमेन्टेसन इन लाइक रियल केस। तर नेपालको कन्टेक्समा चाहिँ प्रब्लम हाम्रो के हो भन्दा आई गेस हामीसँग फ्रेमवर्क नै प्रपर फ्रेमवर्क नै राम्रोसँग बनिसकेको छैन होइन। जस्तो हाम्रोमा चाहिँ जस्तो तपाईँले जापानमा भन्नुभयो रजिस्ट्रेसन गर्न जाँदा म्युनिसिपालिटीमा दिन्छ, तर हाम्रोमा त छैन नि त। हाम्रोमा त डेटाबेसै छैन, रजिस्ट्रेसन नै छैन, सिस्टम नै छैन। त्यो भएर त जस्तो यदि म्युनिसिपालिटीमा रजिस्ट्रेसन गर्ने हो भनेदेखि त सेन्सस गरिरहनु पर्ने त आवश्यक हुँदैन नि त। तर हाम्रो केसमा चाहिँ आई थिङ्क वी स्टिल निड टु ह्याभ अ प्रपर फ्रेमवर्क फर्स्ट। अनि जस्तो डिजास्टरमै पनि तपाईँको रिस्कमै जाने हो भने पनि सिटिजन साइन्स भन्दा पहिला चाहिँ डिसिजन मेकरहरू यसको बारेमा अवेर हुनु जरुरी छ जस्तो लाग्छ। किन भन्दा यदि डिसिजन मेकर जस्तो गभर्मेन्टको पोजिसन्स प्लस अब पोलिटिकल लेभलमा उनीहरूलाई राम्रोसँग आइडिया भयो, यदि होइन यस्तो रहेछ यस्तो गर्नुपर्छ भन्ने थाहा भयो भनेदेखि आई डोन्ट थिङ्क दे हेभ एनी प्रब्लम डुइङ द्याट होइन। इट्स नट द्याट दे डोन्ट वान्ट टु, इट्स जस्ट दे डोन्ट रियली अन्डरस्ट्यान्ड इट्स इम्पोर्टेन्ट अर दे डोन्ट नो। इन मेनी केसेस लाइक लोकल गभर्मेन्टमा जाने हो भने हाम्रो वडा अध्यक्षदेखि लिएर लोकल गभर्मेन्टमा काम गरिरहनु भएको साथीहरूलाई चाहिँ कति कुरा थाहा हुन्न, त्यो हामीलाई पनि थाहा हुन्न, जस्तो लोकल गभर्मेन्टको कम्प्लेक्सिटिज मलाई पनि त थाहा हुन्न, त्यो आफ्नो फिल्ड नहुने भएर चाहिँ आई थिङ्क इट्स इम्पोर्टेन्ट टु मेक देम अवेर एन्ड फ्रम देयर आई थिङ्क दे क्यान टेक इट फर्दर. तर इट्स अ डिफिकल्ट क्वेसन एक्चुअली, आई डोन्ट रियली हेभ एन्सर. अनि यसलाई रिस्कमा जस्तो हाम्रो मोडलहरूलाई रिस्कमा लैजानलाई चाहिँ मेन ल्याकिङ भनेको भल्नरेबिलिटी हो. वी डोन्ट रियली नो द भल्नरेबिलिटिज. अरू त रिस्क त मोस्टली हाजर्ड त होइन, त्यसमा चाहिँ इलिमेन्टेड रिस्क पनि होइन. कहाँनिर बिल्डिङ छ, कहाँनिर मान्छे बस्छ, त्यति त इन्फर्मेसन छ, तर कति भल्नरेबल छ भन्ने चाहिँ राम्रोसँग थाहा हुन्न. अनि त्यो भल्नरेबिलिटी म्यापिङ भनेको चाहिँ एकदम कम्प्लेक्स टास्क हो. जस्तो हामीले युजली अलिक मैले अस्ति एउटा टकमा गएको थिएँ, त्यो वाज सेइङ कि जस्तो युजली पिपल थिङ्क पोर पिपल आर भल्नरेबल होइन, जस्तो गरिब मान्छेहरू चाहिँ उनीहरू भल्नरेबल छ भनेर सोच्छ. बट दे आर वे मोर रेजिलियन्ट बिकज किन भन्दाखेरि उनीहरूलाई चाहिँ बााउन्स ब्याक हुन धेरै टाइम लाग्दैन. तर यदि सोसियली धनी मान्छेहरूलाई चाहिँ यदि डिजास्टर भयो भनेदेखि बााउन्स ब्याक हुन धेरै टाइम लाग्छ कम्पेयर टु गरिब मान्छे. त्यो कुराहरूदेखि लिएर नेपालको कन्टेक्स्टमा त अझ इट्स भेरी डाइनामिक होइन. तपाईँको चाहिँ सोसियो इकोनोमिक कन्टेक्स्ट नै यति छिटो चेन्ज हुन्छ कि इट्स भेरी डिफिकल्ट टु डु द्याट. सो बट द्याट्स अल आई नो. अब कसरी गर्ने चाहिँ आई डोन्ट नो, नट स्योर.
मैले मेरो सानो एक्जाम्पल भने, एउटा सानो,
हजुर हजुर
अशोक पनि अहिले नेदरल्यान्डमै पढिरहेको भएर मैले पनि नेदरल्यान्डमा आइएचईमा पढ्दाखेरि
हजुर
त्यहाँको प्रोफेसरहरूले एउटा के भन्नुभएको थियो, म 2 महिना त्यहाँबाट कोर्स पढ्न गएको थिएँ होइन. भेरी इन्ट्रेस्टिङ छ, अरू अडियन्सलाई पनि इन्ट्रेस्टिङ हुन्छ. त्यहाँ म वाटर रिसोर्स प्लानिङ पढ्दै थिएँ. त्यहाँ हामीलाई एउटा कस्तो त्यो केस सिमुलेसन गरायो भन्दाखेरि त्यो त्यहाँ डाइकहरू धेरै बन्छ सीमा होइन. अब त्यो डाइकको म्याक्सिमम प्रोबेबल फ्लड कति लिने भनेर त्यहाँनिर चाहिँ त्यो हाउसमा हाम्रो जस्तो अब डिसिजन सपोर्टको कुरा गर्दाखेरि अब अलिकति डिसिजन लेभलमै काम गरिरहेको भएर मैले जोड्न खोजेको चाहिँ भनेको हायर लेभलको डिसिजन डिपार्चर भनेको पोलिसी लेभलबाट हुन्छ, त्यो गर्ने भने पोलिटिसियनले हो क्या. अनि त्यहाँ नेदरल्यान्डमा चाहिँ के भन्नुभयो प्रोफेसरले भन्दाखेरि चाहिँ हाम्रो हाउसमा यति रिगरस डिस्कसन हुन्छ अरे, एउटा गाइडलाइन बनाउनु पर्यो भने फ्लडको कति तपाईँले चाहिँ प्रोबेबल फ्लड लिने भन्ने कुरा चाहिँ यति रिगरस डिस्कसन हुन्छ अरे कि हाउसमा. त्यहाँको मेम्बर अफ पार्लियामेन्टहरूले हाउसमा 500 वर्ष लिने कि 100 वर्ष लिने कि 200 वर्ष लिने कि भन्ने कुरा हाम्रोमा चाहिँ यहाँनिर यो भएन र ऊ भएन भन्ने डिस्कसन गर्नुहुन्छ हाउसमा, सानो एजेन्डामा डिस्कसन गर्नुहुन्छ भने त्यहाँ चाहिँ एकदम साइन्टिफिक यस्तो एजेन्डामा डिस्कसन हुन्छ र एक्सपर्टहरूलाई बोलाइन्छ भनेर त्यहाँ भन्नुभएको थियो क्या प्रोफेसरहरूले. मैले ठ्याक्कै त्यही सम्झेँ क्या अहिले तपाईँले भनिरहँदा. त्यसलाई मैले कम्प्लिमेन्ट मात्रै गर्नु. त्यो भएर हामीले अलिकति सेन्सेसाइजेसन, तपाईँहरूले गरेको रिसर्चको डिसिमिनेसन, त्यस्तो कुराहरू चाहिँ हामीले चाहिँ हाम्रो पोलिसी लेभलमा पनि एडभोकेसी गर्न पर्यो कि. मेरो भनाइ त्यति मात्रै हो. यो ठाउँमा पहिरो जान्छ भनेर हामीले जस्तो कुनै एउटा पर्टिकुलर ए भन्ने पालिकाको पुरै ल्यान्डस्लाइड म्यापिङ गरौँ, सबै हेजार्ड निकालौँ, हरेक कुरा गरेपछि त्यो चिजलाई हामीले डिसिमिनेट गरेपछि त त्यहाँ त तपाईँले पहिरो जाने ठाउँमा कसैले तपाईँले प्लटिङै गर्न गरे पनि मान्छेले जग्गा किन्दैन नि त. भनेको इन्डिभिजुअलले नकिनेपछि उसले त त्यो बिजनेस गर्न सक्दैन. भनेको त्यो चिजको सेन्सिटाइजेसन गर्न चाहिँ तपाईँहरूले गरेको रिसर्चलाई हामीले चाहिँ अलिकति पोलिटिकल लेभलको मान्छेहरूलाई सेन्सिटाइजेसन गरेर त्यसलाई हामीले अलिकति जोड्नुपर्छ कि भन्ने मेरो कम्प्लिमेन्ट मात्रै हो. धन्यवाद.
त्यो आई फुल्ली एग्री. यस्तो हो कि अब सबैलाई सबै कुराको नलेज हुँदा, जस्तो मलाई नि त अब पोलिसी लेभलको कुरादेखि लिएर कानुन कसरी बनाउने त्यो कुराको आई डोन्ट नो कसरी इन्फोर्स गर्ने भनेर होइन. सो आई थिङ्क इट्स बेटर इफ द गभर्मेन्ट वुड कोलाबरेट विथ द पिपल हु आर वर्किङ अन इट. तर त्यो चाहिँ अब मोस्टली प्रोजेक्ट थ्रु नै भयो. त्यसपछि यो त्यो कन्सेप्ट नभएर, बट आई गेस इट विल इम्प्रुभ सुन. आई होप इट विल इम्प्रुभ सुन. अर्को क्वेसन चाहिँ आई थिङ्क प्रतीक, ग्रेट प्रेजेन्टेसन, थ्याङ्क यू प्रतीक. अर्को क्वेसन कहाँनिर थियो? रोशन यादव आई गेस.
यो क्वेसन सायद कन्टेक्स्ट अर्कैतिर सोध्नु भएको हो कि जस्तो लाग्यो.
Plants are planted to prevent landslide. Yes, मिटिगेसनको लागि चाहिँ प्लान्ट्स you can, but mostly for shallow landslide. If it is deep-seated, it can be even counterproductive. And yeah, you can do that. From what plant's name it is, I'm not sure. It actually helps. Like प्लान्टले गर्ने चाहिँ के हो भन्दाखेरि रुटको कोहेसन तिम्रो चाहिँ जस्तो प्लान्टको जराले चाहिँ स्यालो ल्यान्डस्लाइड हो भनेदेखि चाहिँ त्यो सोइललाई समातेर राख्ने हो हैन। तर डिप सिटेड हो भनेदेखि चाहिँ प्रब्लम के हुन्छ भन्दा डिप रुट भएको प्लान्ट छ भने त्यसले तल गएर झन् क्र्याक फर्मेसन गराउन सक्छ। त्यो भएर चाहिँ इट डिपेन्ड्स कस्तो खालको ल्यान्डस्लाइड कस्तो खालको प्लान्ट त्यसमा डिपेन्ड गर्छ। आइ एम नट स्योर विच प्लान्ट हो।
ओके, भनेपछि अब हामीसँग एडिसनल क्वेसनहरू सायद छैन नै जस्तो लाग्यो मलाई। अब सरी हामीसँग सुरुदेखि नै अहिलेसम्म एक्टिभली पार्टिसिपेन्टहरू हुनै हुन्छ, एबभ 30 पार्टिसिपेन्टहरू। सो अडियन्सहरूलाई पनि धन्यवाद दिन चाहन्छु। र यो इन्साइटफुल टपिकमा चाहिँ प्रेजेन्टेसनको लागि म अशोक दाइले चाहिँ एनजिएसको तर्फबाट हार्डली थ्याङ्क यू भन्न चाहन्छु।
मेरो नि थ्याङ्क यू एनजिएसलाई बोलाएको।
एन्डिङ द सेसन लास्ट फ्यु वर्ड्स के छ भने तपाईँले राख्नु अनुरोध गरे।
हैन, थ्याङ्क यू फर एनजिएस टु इन्भाइट। इट्स नाइस टु कम ब्याक एन्ड टक अबाउट थिङ्स। I don't really do anything, but it's better to just talk.
Thank you, Ashok Dai.
Thank you.
For now, आजको एपिसोड चाहिँ हामी यहीँ इन गर्छौँ। प्रेजेन्टेसनको लागि अशोक दाइ र जोइन हुनुभएको तपाईँ सबैलाई धन्यवाद भन्न चाहन्छु। र हाम्रो नेक्स्ट 12th एपिसोड चाहिँ लाइडार सर्भिङ एन्ड म्यापिङ इन नेपाल फ्रम इन्जिनियर गणेश प्रसाद सिग्देल सरबाट हुन्छ। यहाँहरूलाई त्यो विषयमा पनि आउने फ्राइडे भन्दा नेक्स्ट फ्राइडे आफ्टर 14 days तपाईँहरू जोइन हुन सक्नुहुन्छ सेम लिङ्कमा। त्यसको लागि पनि इन्भिटेसन गर्न चाहे एनजिएस तर्फबाट। र आजलाई भने चाहिँ हामी एपिसोड यहीँ अन्त गर्छौँ। सबैलाई चाहिँ अब गुड नाइट गुड मर्निङ अब जहाँ हुनुहुन्छ त्यो भन्दै चाहिँ फर नाउ अहिले चाहिँ हामी बिदा हुन चाहन्छौँ। थ्याङ्क यू।
थ्याङ्क यू सर भाइ सर।